Hello, this is going to be the first lecture for the summer session of MEC 3820 heat transfer. We'll begin with a discussion of temperature. As you would know from thermodynamics and from chemistry, temperature is a measurement of the internal kinetic energy of a substance. When we talk about kinetic energy, we're referring to molecular motion. For a gas, we will have translational motion, rotational motion, and vibrational motion, but for a solid, there will only be rotational and vibrational motions. Now, absolute zero is a theoretical temperature. It's the temperature at which all molecular motion ceases, when the actual molecule or atom has no energy. So that's a theoretical, it's relatively, or I think theoretically impossible for you to reach absolute zero, but it works as an absolute temperature scale for us. So we will be dealing with the SI system. Specifically, we will deal with Kelvin and Celsius. So Kelvin is the absolute scale referenced to absolute zero, and Celsius is a relative scale used for and essentially defined between the freezing point and boiling points of water. So when we're talking about temperature measurement, right, we need a device, and right, we are all familiar with the standard thermometer. So we want, ideally, for these devices to have a linear response. So to get the Celsius scale, we will measure the freezing point of water on our device, and we'll measure the boiling point of water. And then you divide that span by 100, and that defines your degree. And that degree is the same whether you're working for the Kelvin system or the Celsius system. So it's different for the Fahrenheit system, but we are going to be sticking to the SI system because the SI system has the Celsius is defined through a physical parameter. All right, so there is a relationship between the two scales. Absolute zero is defined as negative 273.15 degrees Celsius, or 273.15 degrees below the freezing point of water. So if you want to convert from Celsius to Kelvin, you need to add 273.15 degrees to it. All right, so let's take a look and kind of apply these things. This is again kind of going back to your thermodynamics. So consider a specific mass. So we have a cube of mass. It has a temperature of 50 degrees C, which is 320.15 degrees Kelvin. Now we can add energy to the mass such that its internal energy, its internal kinetic energy increases, and that will result in an increase in temperature. We're not going to matter right now how we're adding the energy. We're just going to suffice to say that we're adding energy to the system. And at this point, we will say that we've increased the temperature by some delta T. And that delta T is going to be the same regardless of whether you're working in the Celsius or the Kelvin scale. Now that's really important to know because a lot of the work that we're going to be doing in this class, we will be talking about raising the temperature of something or cooling the temperature of something. And when you're starting from T1 to go to T2, that's a delta T. So it doesn't matter whether you're in the Celsius scale or the Kelvin scale because their definitions for the degrees is the same. And when you measure the temperature, you're measuring the internal kinetic energy of a substance. And if a change in the temperature is a means to quantify either the change in internal energy of a substance or the difference in internal energy between two substances. So you could take the temperature of block 1 and the temperature of block 2. The delta T between those two would give you the change or the difference in energy between those two substances. Or if you measure the temperature of block 1 and you measure the temperature of block 1 after you've added or subtracted energy to it, that will talk about the change in your internal energy. So let's take a look at an example. We have the total thermal energy in a 2.5 kilogram block of 316 stainless steel, and we're looking at that total energy at its temperature of 50 degrees C. So we'll note that 316 stainless steel has a specific heat of 468 joules per kilogram per Kelvin. Right? It's important that we remember how to state this, right? So 468 joules per kilogram, And what does the per Kelvin mean? It means that if you have 1 kilogram of this material and you want to increase it 1 degree Kelvin, you need to add to it 468 joules. And specific heats of different materials are located in the back of our textbook in table A1, so you really should get familiar with our tables. So the total thermal energy is an absolute quantity, right? So we can now take a look at how much total energy is in this block. Now what we need to do is, since we're looking for the total energy, that's an absolute quantity. It's not a delta T. So we need to convert the 50 degrees C to Kelvin. So we are going to use m dot, or rather m, right? We'll be from, you see how I almost made the mistake of going over it, right? We're not looking for the rate of energy flowing through something, which would be back from fluid mechanics, m dot c sub p delta t. Now we're basically in thermodynamics. What is the total energy? So it's the mass of the object times its specific heat times its current temperature in absolute scale. So we have 2.5 kilograms of material. Its specific heat is 468 joules per Kelvin per kilogram. And then we multiply it by 50 degrees, but we have to convert that to its absolute temperature. So we add 273.15 to that, and that gets us Kelvin. So we end up with the total thermal energy inside this 1 kilogram block, or 2.5 kilogram block rather, is 378,068 joules, or 378 kilojoules. Now again, that's a lot, feels like a lot of energy, but again, it's referenced to absolute zero. So basically everything at 50 degrees or 40 degrees or 30 degrees Kelvin has so many kilojoules of energy located within it. So here's a second example. Now, what is the amount of energy required to increase the temperature of this 2.5 kilogram block of stainless steel from 50 to 55 degrees? Now, in this case, we're not dealing with an absolute temperature, we're dealing with a change in temperature. So it doesn't matter. I don't have to convert 50 degrees and 55 degrees to Kelvin, because when I subtract the two, I would just be subtracting off that conversion factor of 273.15. So in this case, it's mass times specific heat times the delta T, which is just 5 degrees. I have this thing over here written as like my own notation, because sometimes I don't really use it much now, but this is just to say that the degree Celsius and degree Kelvin are both the same when you're doing a delta T, because what's going to happen to some of you is that you're going to look in the back of the book and your specific heats are going to be given as per degree Kelvin, and you're automatically going to assume that you need Kelvin up here to cancel your units. Well, you don't, because while the specific heats are all given, the parameters for these materials are given on a per Kelvin basis. They are there for if you're using an absolute scale, right? If you're trying to figure out the total amount of energy in the substance, you have to use Kelvin. But if you're just dealing with a change in energy, and you're given your temperatures in Celsius, there's no need to change them. So in this case, just to change it 5 degrees, we would need to increase its energy by 5.85 kilojoules. All right, so it's good to talk about energy now. So while the top of this slide is talking about thermal energy, we need to take a look at all the different types of energy that we've seen. Well, we have mechanical energy that shows up in physics, materials, applied strength, fluid mechanics. So our mechanical energy, right? So it's spring energy, we have kinetic energy of the actual particle moving, and we have stored energy from the gravitational field, stored energy in a spring, and we look at the mechanical energy in materials, and we talk about strain energy, but strain energy is really just spring energy, right? We take a load, we put it onto a beam, and if we stay within its elastic limit, when we let it go, the energy will come back. But if we keep doing that, and you've all had this idea, this you should have all at some point taken a paper clip or something and push it back and forth, and you'll recognize that it gets hot. So not all the energy is coming back, especially if you plastically deform your object. And in that case, their energy that you put into it to deform, some of that goes into thermal energy. And in fluid mechanics, right, we deal with mechanical energy all the time. We have the velocity of the fluid, and we can talk about hydrostatic pressure being converted directly to velocity. But the question is, what does pressure come down to? So some of the pressure is due to the weight of the object, but we also need to take a look at the pressure, like the pressure of a gas is due to its translational internal energy. So there's where we're talking about thermal energy. So again, with materials at a constant temperature, we can pull the sample, right, in an Instron machine, and we would find out that the work done, the force times the change in length here, where does that, is it doesn't come back, right? When we apply this, this is where we're physically deforming it. So where did that work go? That work, right, newtons per meter, goes into internal energy, so it gets lost, right? But what do we mean by lost? It's not the mechanical energy is lost because it doesn't come back to us as mechanical energy. It gets lost, meaning it gets transferred into internal energy, which is thermal energy. And fluid mechanics, a classic case of the rocket engine, is that if I have a vessel that contains air or some gas at say 101 kilopascals, its velocity is 0. Now if I let that expel into a vacuum, we know from Bernoulli's equation that we're going to have a set velocity of the gas coming out. But why is the gas moving? Where did that kinetic energy come from? Well, that kinetic energy is, the phrase can be stated that you're taking random thermal energy in terms of pressure and converting that into directed kinetic energy. That is the basis, if you want, of how a rocket engine works. So a rocket engine, of course, does combustion to create very, very high pressures, but when it's exiting out through a nozzle, where you're taking random thermal energy and converting it into directed kinetic energy. Okay, same thing. Now we're getting closer into thermal energy. In thermodynamics, we have PV equals RT, and the PV is the increase in translational energy results in more impacts per unit time, so higher pressure. So if I keep the pressure the same but decrease the volume, or if I keep the volume the same and increase the pressure, that's going to cause an increase in the internal energy of the substance. So you've often looked in terms of this in terms of the ideal gas law. Well, now you got to remember, the ideal gas law assumes that all the energy of the particles of the gas are completely translational. So basically, when you're using the ideal gas law, you're neglecting the rotational energy and the vibrational energy of the molecules. That's why ideal gas law works well for simple gases like hydrogen and helium, but it gets increasingly worse as you get into diatomic molecules such as oxygen and nitrogen, and it becomes really bad when you get up into hydrocarbons, because at that point the energy that you're putting into the substance to, i.e., increase its pressure, becomes so much that you are actually losing a lot of that energy. It doesn't go straight into pressure, which would be the translational energy, but a lot of it's going to go into its rotational and vibrational energy. So if you put in like 100 joules, well, maybe 50 joules of it goes into translational, and 25 joules each go into rotational and vibrational energy. So you might be off in your calculation by 50%. All right, so again, thinking about how thermal energy works. So again, our classic piston, right? So if you have a piston here that has an area A and you want to move it through a set distance, say delta L, and so this would be work done at constant pressure. So you input thermal energy in order to maintain this as a constant pressure. The volume of the piston needs to increase. So what that basically is, think of it, it's the pressure times the area is a force, right? PA times F is a force. And then that force acts through a distance delta L, which is work. So force times distance is work, and that gives you your PDV work. So you should have all been very familiar with this from thermodynamics, but it is just a good thing to remind you that PDV, right, which is basically up here, PDV work refers to an increase in thermal energy. So PDV is work, work is energy, right? Work causes an increase in our classic dynamics. Work kinetic energy theorem is that when we do work on a particle, its thermal energy increases, or kinetic energy increases. But in this case, if we do work on a gas or some other type of substance, we can also cause its internal energy to increase. Okay, so just to summarize kind of here, we have the temperature as a measurement of thermal energy. Thermal energy is given in joules. We can measure our temperature in either degrees Celsius or in the absolute scale Kelvin. Thermal energy of an object can be increased by mechanical means. So we have shaft work, friction work. We can the conversion of internal energy can be done through a chemical means, right? We have a battery, nuclear. All right, so chemical or nuclear potential can be directly converted into thermal energy, and we can also convert electrical energy. Now, again, if we put a battery to this, right, the battery is going to, through a chemical means, is going to create an electric current, and then the electric current can be allowed to run through a resistor that will then give off thermal energy. So you have to remember, in a situation like that, the battery in its conversion is also not 100% efficient, so the battery is losing some energy to thermal energy as well as creating currents. So this is where these inefficiencies of an object or a system will come in. And what we're going to be looking at in the next video will be, how do we transfer thermal energy? And there's three main modes. There's conduction, convection, and radiation, and we'll refer to these as the modes of heat transfer.